two choices for chapter 14. Chapter 14, I could cut it at the ideal gas law and the special calculations, and then put this stoichiometry stuff on the next exam, or I can include the stoichiometry.
If you can cut it and put it on the next exam, I think it'll help a lot. That's a lot of material to cover
All right.
in a day.
Yeah, I'm going to cut it then. The chapter 14 is going to just cover through molar volume. So gas stoichiometry will not be on the test. So molar volume, next section is that. Yeah. So 14.6. Molar volume. And then 14.7 starts to do with stoichiometry, chemical reactions. The exam's 3. So up to and including 14.6. We're going to start chapter 15 today. There's not much more to talk about chapter 14. Yeah. Use some more examples. Okay, are there other questions? We did this problem in class, except we didn't do STP, standard temperature. We did standard pressure, but not standard temperature. Standard temperature is 0 degrees C. We use room temperature instead of standard pressure. And so it's just a stoichiometry problem. We're going to go from grams of zinc to moles of hydrogen to liters of hydrogen here. So grams of zinc, moles of zinc, moles of hydrogen, using the equation up here. And then we went directly to liters of hydrogen. We can go from moles to liters if we know the molar volume. The 22.7 liters per mole, this is a number of people memorize. This is for any gas, not just hydrogen, any gas. But this one's not as useful because of the temperature. What's more useful is the one that we calculated yesterday, which was 24.79 liters per mole of any gas. That would give us a larger volume here. So, but that's not the only way to do the stoichiometry calculation. This is the molar volume method. There's another way of doing it as well, which we'll talk about. The other way of doing it is this way. We stop at moles of hydrogen. We stop at moles of hydrogen, and then the pressure and the temperature are given. And so we could use the ideal gas law to determine the volume of hydrogen. That is, we'll do a separate algebraic calculation here rather than a dimensional analysis chain. This is an alternate way to do it. All right, how many liters of CO2 measured at 744 torr, 131 degrees C will be produced by the complete burning of 16.2 grams of gaseous butane? That's the equation there. And so in this case, we're not at standard temperature, we're not at room temperature, and we're not at standard pressure. And so we're going to have to figure out what it is. In fact, the molar volume is going to be quite big because the pressure is lower than normal pressure, 2, the temperature is greater than. So the lower pressure means gases expand, higher temperatures mean gases expand. And so one of the things we could do is we could just calculate the molar volume right now. Molar volume is equal to the volume per mole of V over N. You know, there are different ways we can generate this equation. I showed you one derivation yesterday. Another derivation is this, in RT. We want to put V and N on the same side. We want to put V and N on the same side. We'll divide by P, and we'll divide by N. So this gives us V over N is equal to RT over P. And that's the molar volume. So this is just equal to RT over P. And so we could just do a quick initial calculation to figure out what the molar volume is. R is 0.08206 liters times atmosphere per mole times Kelvin. T is 298. Oh, actually, this is not 298. I'm just in the habit. It's 131 degrees C. So 131 plus 273 makes 401. 404. Yeah. 404. 404. We could do the 0.15 or 0.15 Kelvin. So oftentimes it's left off. Just introduces a small error. We leave that 0.15 off. Will be reduced by the. Okay, so we just need the pressure here. The pressure is 744 torr, and the conversion factor is 1 atmosphere is exactly equal to 760 torr. So that's exact. Anyway, we have 3 sig figs we're allowed in the smaller volumes. What does it come out to here? So 0.08206 times 404.15 divided by 744 and then times 760, since I'm going to invert that fraction and multiply. And so the molar volume is 33.87 liters per mole. The molar volume increased. One, the temperature is a lot higher than room temperature. 2, the pressure is lower. So the volume is a lot bigger, 33.87 liters per mole of any gas. All right, now we have the molar volume. What we're going to do is we'll just map this out. So we're going to start off with grams of butane, C4H10. Butane is 4 carbons, no double bonds, so what we call an alkane or hydrocarbon. So we'll go from grams of butane to moles of butane, standard stoichiometry. The moles of butane to moles of CO2, using the balanced chemical equation, and the moles of CO2 directly into liters of CO2 gas, because we just calculated the molar volume under these conditions here. And so starting off with the grams of butane, we have 16.2 grams of butane, C4H10. And so to convert that into moles, we'll need the molar mass. So we have 4 times 1201, that's the carbons. So it's 4804 grams worth of carbon. And then we have 10 hydrogens, which is 101. So this is going to be 10. So this is going to give us 58.4 grams per mole. So 58.14 grams of C4H10 per mole. C4. So the grams cancel out the grams. Now moles. So we're just going to go from moles of C4H10 to moles of CO2. It's a 2 to 8 ratio. So 8 moles of CO2 for every 2 moles of C4H10. Although I could simplify it, 4 to 1 ratio. I'll just leave it as an 8 to 2 ratio. All right. If I stop here, I have moles of CO2. Well, if I have moles of CO2 and I know the pressure and I know the temperature, then I can just plug it into the ideal gas law. And so one option is to stop here. So if I stop here, then I can calculate the volume by plugging in the moles I could do a separate calculation for volume. That's one. Or two, we just continue on. Two, I have to do a separate calculation for molar volume. So I do the separate calculation for molar volume here, and I see it, I have 33.87. 33.87 liters for every mole of gas. This is for any gas. And so either way, we do a separate calculation. My preference is option 2. My preference is option 2 because C4H10 is a gas as well. And so if they give us the volume of gas here rather than the grams of gas, then if I use option 1, I have to do 2 separate calculations because if they give us the volume of gas, then I have to calculate the moles of gas. So I have to do an ideal gas law type calculation, solving for moles of gas, and then plug it in here, and then I have to do another ideal gas law calculation to figure out the volume of CO2. However, if I use option 2, I only have to calculate the molar volume once, so I could use it for C4H10, and I could use it for CO2 because the molar volume works for any gas. So option 2 is the better option. Well, anyway, let's go ahead and calculate how many liters of CO2 is generated here. And so we go 16.2 divided by 58.14 times 8 divided by 2 times 33.87. 37.7. So we get 37.74 liters. In other words, 37.7 liters of CO2 gas. So let's take a look at this solution here. So they calculated the molar volume. We got 33.9 to 36 bigs. I didn't round it there. Just went ahead and carried next to that. Then they set up the math: grams to moles, moles to moles, moles to liters. Calculated molar mass 58.12. We got 58.14. There's a slight difference there if you can round off. And they calculated 37.8. I got 37.7. So this difference is rounding. That's it. All right, this is called the molar volume method. This is the ideal gas method. So, the ideal gas method for stoichiometry is we stop here. So this is, option 1 is called the ideal gas method, where we use ideal gas law. Option 2 is the molar volume method. My preference is the molar volume method, but you want to do it the way you want. And so this is doing the exact same problem using the ideal gas method. The only difference is they stop. You see they stop here once we hit moles of CO2. They stop there once you hit moles of CO2, and then we have N of CO2. 1.11 moles of CO2. And then they plug that into the ideal gas law because we have N, we have P, we have T. And so they solve for volume. Volume is equal to nRT over P. Plug in the numbers. N is 1.11. And then they're using this R. This R is for torr. If you want, you can memorize it. So they get 37.6 liters, which is slightly different because earlier they got 37.8 liters, right? And what do you think that's due to? This is due to differences in rounding. They did a couple of intermediate rounding steps here. And so those are two methods. Either one's fine. I don't care which one you use. All right. This is the volume to volume. Volume to volume is super easy. If on the other hand, let's say they gave me two liters. If I combusted 2 liters of butane under this pressure and temperature, how many liters of CO2 would I get? If I combusted 2 liters of butane, how many liters of CO2 would I get under the exact same conditions? Avogadro's law says that the mole ratio is the same as the volume ratio. That is, volume is directly proportional to the number of moles. So what that means is if I combust 2 liters of butane, I'm going to get 8 liters of CO2. If I combust 10 liters of butane, how many liters of CO2 would I get? It would come out actually 40 liters because just the way it works. And so that's the volume to volume method. So let's take a look at that. It's Avogadro's. So Avogadro's law states that the gas volume is directly proportional to the moles at constant temperature and pressure. We have to make sure it's constant temperature and pressure. So the ratio of moles is the same as the ratio of volumes. In other words, the mole ratio is the same as the volume ratio. And so we can do volume to volume conversions, just like we do mole conversions. But there's one caveat, there's one restriction. It has to be a constant temperature and pressure. Otherwise, if the reactants are different temperature and pressure than the products, then it's not going to work. All right, so let's take a look at this problem. This is sulfur, solid sulfur. This is a gas. This only works for gases, right? The same thing with the molar volume. The molar volume of solids and liquids is totally all over the place. A mole of liquid water only is 18 milliliters. 1 mole. Whereas 1 mole of gaseous water, steam, is a lot more like 25 liters. So it is found that 1.75 liters of O2 measured at 24 degrees C at 755 torr is used in burning sulfur. So we have 1.75 liters of O2. Now, 1 point in the exhaust hood, the sulfur dioxide produced is at 165 and 785 torr. Find the volume of SO2 under those conditions. So this is a bit trickier because what happens is that the temperature and the pressure aren't the same. The temperature and pressure are different. Temperature and pressure are different, then we can't do it. If the temperature and pressure were the same, then 1.75 liters of O2, it's a 1-to-1 mole ratio. That means it's a 1-to-1 volume ratio. And so 1.75 liters of O2 completely reacted will form 1.75 liters of SO2. 1-to-1 mole ratio, 1-to-1 volume ratio. But that's under those conditions there. And so there are 2 ways we could solve this particular problem. One way is we just do this. There are multiple ways to solve this problem. One way is we can go from liters of O2 to moles of O2. But we need the molar volume at 24 degrees C and 755 torr. And then we go from moles of O2 to moles of SO2. And And then for moles of SO2, we go to liters of SO2. But here, unfortunately, we need to recalculate the molar volume because the molar volume now is going to be at 165 degrees C and 785 torr. And so this is one way of solving this problem. Another way of solving this problem is like this. The other way of solving this problem is if we do liters of O2 and go to liters of SO2. Okay, the liters of O2 will be at 24 degrees C and 755 torr. And the liters of SO2 will be at 160, no, we can't do it. It has to be at the same, because the temperature and the pressure have to be constant, so that means this has to be 24 degrees C and 755 torr. Otherwise, we can't use the mole ratio that's given. And so, well, that's not the temperature and the pressure that we want. And so the temperature and the pressure that we want is different. And so what we do is we do a second calculation. Once we have this, then we do combined gas law. That is P1 V1 N1 T1 is equal to P2 V2 N2 T2. And so what we're going to do is, okay, this conditions, 1 will be 24 degrees C, 755 torr. And then conditions 2 will be at 165 degrees C and 785 torr. And so what we'll do is we'll just do this, where we change the temperature, we change the pressure, and see what happens to the volume. So that would be the combined gas law. So which one's easier? I don't know. You know, 1 or 2. You could do the standard stoichiometry setup, or you could do it the combined gas law. Since this is in the Avogadro section, I think they want us to do it the combined gas law method. Right? And so we're going to try the combined gas law method. They started off with a hard one. Most of the problems are the same temperature and pressure. Most of the time we don't have to worry. It's just a straight volume to volume conversion. Okay, the first step of this is pretty easy. Okay, if we start off with 1.75 liters of O2, then the equation there is this. For every liter of SO2, I'm going to have to consume 1 liter of O2. It's a 1-to-1 mole ratio, it's a 1-to-1 volume ratio at constant T&P. And so this is at 24 degrees C and 755 torr. And so this is going to give me 1.75 liters of SO2 at 24 degrees C and 755 torr. But what happens if the temperature increases? If the temperature increases, what's going to happen to the volume? It's going to expand. It's going to grow bigger. So the temperature increased, but the pressure increased also. If the pressure increases, that's going to shrink it. So the temperature is going to expand it, the pressure is going to shrink it. So let's see what happens here. And so what we're going to do is we're going to do combined gas law. We're going to solve for V2. V2 is equal to P1 over P2, and then T2 over T1, and then N2 over N1, and then times V1. And so let's look at the first ratio. P1 and P2. Well, P2 is bigger than P1. Do you see that? And so that means if P2 is bigger, that means it's going to shrink the volume. And then let's look at the next ratio, T2 versus T1. T2 is bigger than T1, that's going to increase the volume. Did the number of moles change? No. And so the number of moles didn't change. N2 is equal to N1. We didn't remove any gas, we didn't add any gas. So for example, if we added gas, N2 is bigger, that means V is going to grow bigger. If we remove gas, then N2 is smaller. That means the volume is going to shrink. And so let's just plug everything in here. Okay, do we have to convert this into atmospheres? No, the answer is no, because the units are going to work out anyway. And so this is going to be, P1 is 755 torr, and P2 is 785 torr. So the torr cancel. Do we have to convert it into Kelvin? Well, the units cancel out degrees C, but there's a big problem. What if it's 0 degrees C? If it's in the numerator, it's okay, but if it's in the denominator, yeah, if it's in the numerator, we get 0 volume. That mathematically goes okay, but if T1's 0 degrees C, which is a possible temperature, then this is undefined. And so the temperature must be in Kelvin. And so what is T2 in Kelvin? T2 is 165 plus 273. This is 165 plus 273, I want to think, it's 438 Kelvin. So T2 is 438 Kelvin. T1 is 24. 25 is 298, 24 must be 297. 297 Kelvin. The Kelvins cancel. Times V1. V1 is 1.75 liters. So I'm going to do the calculation now here. It's going to be 755 divided by 785 times 438 divided by 297 times 1.75. 2.482 liters of SO2. So what's going to happen is, at the higher temperature, it expands. This slightly higher pressure doesn't have a huge impact on it, but the higher temperature is going to result in a big expansion of the gas. So again, they did the combined gas law. You see, initial, final, 1, 2. So solving for B2. They didn't use the complete one with the N, The N, and you'll see in Chem 1A, we'll add gas or remove gas, but in Chem 4, you don't usually see it. They say, well, we aren't going to add or remove gas, so N doesn't change. If N doesn't change, just remove it from the equation. And so they're solving this combined gas law from chapter 4, not the complete one. So we got the ratios. They got 2.48 liters. We got 2.482 liters. Rounded to 2.4. They skipped a step though. The step they skipped is the Avogadros. They didn't show the conversion. It's a 1-to-1. If this was not 1-to-1, let's say it's a 1-to-2, then I'd have to double that, right? And so this is kind of deceptive because you're thinking this is O2. This is not O2. There's a 1.75 liters of SO2, not O2. And so we got to pay attention to this here. It doesn't matter how you do it. Let me take that back. They're doing O2. So they're saying 1.75 liters of O2 under these conditions would be how many liters under the new condition? I didn't do it that way. But it doesn't matter. You could do it either here or here. You got to convert one or the other. So at the end, what they did was this. This would be the number of liters of O2 at the higher temperature. And here they do it, the 1-to-1 video ratio. But that 1-to-1 liter ratio is going to be at the higher temperature. It's still 1-to-1, even at the higher temperature.
Just to clarify, so they're applying the Avogadro's law thing, where the liter or the volume is directly proportional to liter. That's what it's on.
Yeah. The Avogadro's law things like this. It's very handy in combustion reactions because we can do these calculations very quickly. And the gas stoichiometry, if we're doing liter to liter and the temperature and pressure don't change. So let's say the temperature is room temperature and the pressure is 1 atmosphere. And then we're looking at this equation, CH4 plus O2. We need 2 O2s. This is going to produce CO2 plus 2 H2Os. CH4 is a gas, CO2 is a gas, O2 is a gas. We have 3 gases here. And so Avogadro's law says this. Let's take 5 liters of methane. 5 liters of methane, how many liters of O2 do I need to completely combust it? But 5 liters of methane, how many liters of O2 do I need? Well, I could go through the full stoichiometry, right? But I'm not. I'm just going to go through Avogadro's because here, if I have 5 liters of methane, I need twice as much O2. If they're all at the same temperature and pressure, then I'm going to need 10 liters of O2. How many liters of CO2 will I form? 5 liters. And how many liters of water will I form? No. I'll not form 5 liters of water. I'll form way less. Not even 1 liter of water will form. Why? Because it's a liquid. This only works for gases. If I need to know how many liters of water form, I have to do it using stoichiometry. And so for everything else, it's easy. You know, this is going to be 5 liters, this is going to be 10 liters, this is going to be 5 liters, but this is going to be what? And so if I want to figure out what that is, then I have to do my standard stoichiometry. The standard stoichiometry would be this. You know, at the heart is the mole-to-mole conversion. And so what I do is I go from liters of methane to moles of methane. I can go liters of methane to moles of methane using the molar volume. Okay? So I'll have to calculate the molar volume. And then from moles of methane, I'll go to moles of water. From moles of water, I'm going to go to grams of water. From grams of water, I'll go to milliliters of water. To go from grams of water to milliliters of water, I need the density of water. The density of water, you should have memorized in 3 sig figs. What is the density of water? The 3 sig figs. 1.00 grams per milliliter. And so if I get 18 grams, it'll be 18 milliliters. 36 grams will be 36 milliliters. But it depends. I'm going to get a lot less than 18 grams of water because it's not a liter. And so, you know what? I know this one. This is 24.45 liters per mole. Or if the temperature were RT and the pressure were 1 bar, then I know this one. It's 24.79 liters per mole. These two are actually pretty useful to know. For you, you should have this one memorized. It's just standard pressure, but the most common temperature here. So we could figure it out. Well, it depends on what conditions we're doing it under. Well, the original conditions were this. So if I do it at, But if I use this, it would be exactly the same thing, 5 liters, 10 liters, 5 liters. So setting up this calculation, we go 5 liters of methane, and then we'll use one of those molar volumes. Okay, let's use the atmosphere's one. And so that's 24.45 liters per mole of 80 gas at RT and 1 atm. It's only valid at that temperature, at that pressure. So that gives me moles of methane. And then I look at the mole ratio there. It's actually, sorry, it's two water. So 2 moles of water for every 1 mole of methane. And then I know the molar mass of water, it's 18.02 grams of water per mole of water. So oxygen 16, 2 hydrogens is 202, 1802. And then the density of water, for every milliliter of water, I have 1.00 grams of water. Figure it out. And so how many milliliters of water am I going to get? Let's see, 5 divided by 24.45 times 2 times 1802. 7.37 milliliters. Or 0.007 liters. 0.007 liters. What we're going to get. This is a trick question. Do you see it's a trick question? Because if I change this to H2O gas, then you would have been right. If I change this to H2O gas, you would have said 5 liters, well, that's correct. But watch out, because you gotta look at the state. We'll do some practice stoichiometry later. Let me crack into chapter 15. Chapter 15 deals with gases, liquids, and solids. These are the 3 states of matter. There's actually a 4th state of matter. Do you know what the 4th state of matter is? Gases, liquids, and solids. Plasma. Usually it goes like this: solids, liquids, gases, plasma. If you start off with a solid, you heat up a solid, eventually it melts, turns into liquid. You heat up a liquid, eventually it vaporizes into gas. You heat up a gas and it turns into plasma. Superheated gas, violent collisions, that kind of stuff. So let's go through a brief rundown of learning objectives here. Given the partial pressure of each component in a mixture of gases, find the total pressure. This is called Dalton's law. And so we're going to do Dalton's law. Just use the equation for Dalton's law, which is a pretty simple equation, actually. 15.2, explain the differences between the physical behavior of liquids and gases in terms of relative distances. This is kind of the particulate visual picture of liquids and gases and solids. Okay. As far as the particulate picture of what a liquid is, a solid is, and what a gas is. For 2 liquids given comparative values of physical properties that depend on intermolecular attractions. So we're going to talk about intermolecular attractions. Intermolecular attractions is a big topic in this chapter. Intermolecular attractions allow us to understand the physical properties of these at a particulate level. Predict the relative strengths of those attractions. or given a comparison of the strengths and the intermolecular attraction, predict the relative values of physical properties. So what we're doing is we're trying to correlate properties with structure. 15.3, identify and describe or explain induced dipole. Induced dipole forces, this is an intermolecular attraction. We call it induced dipole. There are some major intermolecular forces of attraction that we should know. Induced dipole is one of them. These are also called van der Waals or dispersion forces. And then we have dipole-dipole forces or dipole forces and hydrogen bonds. These are the three major types of intermolecular attractions that we look at. There are others too. Given the structure of molecule or information from which it may be determined to identify the significant. So we want to be able to identify when we see these based on the structure of the molecules, what kind of intermolecular forces of attraction exist there. Given the molecular structure of the two substances or information from which they may be obtained, compare and predict relative values. So again, this is just trying to identify what types of intermolecular attractions we can expect based on the molecular structure. 15.4, describe or explain the equilibrium between the liquid and its own vapor. Okay, when something vaporizes, we have what's called a dynamic equilibrium. Or when something melts, we also have a dynamic equilibrium. Equilibrium processes are important in chemistry, so this is our first peek at equilibrium. Okay, so this is looking at what's happening during vaporization at the particulate level. Describe the relationship between vapor pressure and temperature for a liquid vapor system. The equilibrium explains this relationship in terms of kinetic molecular theory. So again, we're looking at vaporization. You know, vaporization is liquid being converted to gas at the particulate level. So that's what we're doing. 15.5, describe the process of boiling. Well, boiling is the same thing, liquid being vaporized. Relationship among boiling points of temperature which vaporizes spontaneously, vapor pressure and the surrounding pressures. We'll look at that. Describe the typical relative density relationship between solid and liquid phase of substance. Usually solids are more dense, except for water. Water is very unusual because ice is less dense. Liquid's actually more dense. So this is one of the big reasons why light exists on this planet. 15.7, distinguish between amorphous and crystalline solids. You know this term amorphous that refers to? Have you heard that before? Crystalline means it's well ordered. Amorphous means there's disorder in the structure. And so when we look at lattices, crystal lattices, they're typically very well ordered. Except for glass. You know, if you look at the lattice of glass, it's not ordered at all. It's somewhat disordered. It's disorder called amorphous. Amorphous means structureless. There is some structure there. Distinguish among the following types of crystalline solids: ionic, molecular, covalent, metallic. Those are the types of forces that hold the particles together. You know, ionic bonds, covalent bonds, metallic. For molecular, we have intermolecular forces. 15.9, given two of the following, calculate the third. So what we're going to do is we're going to look at what we call the thermodynamics of the heat that's involved in going from a liquid to vapor. In other words, we change states, liquid to gas, gas to liquid, solid to liquid, liquid to solid. All those involve energy changes. So we'll be looking at that. Given two of the following, calculate the third. This is all just dimensional analysis using energy changes. Given three of the following, calculate the fourth. Energy. This is 15/10 and more energy changes. Sketch, interpret, or identify regions in a graph of temperature versus energy. This is kind of mapping out how the energy changes. We have these. Remember these delta H, delta B changes? They're introduced a while back. Stoichiometry chapter. All right, this is 1511. So it's a little bit long chapter. Various topics. copy of Spelman's law of partial pressure. The total pressure exerted by a mixture of gases is the sum of the partial pressures of the gases in the mixture. Partial pressure of any individual gas in the mixture is the pressure that the gas would exert if it alone occupied the same volume at the same temperature. Mathematically, P is equal to the total pressure is equal to the sum of what we call the partial pressures. P2, P3. Let's see this in action here. Gas mixtures can be described in terms of composition. When we deal with the composition of a gas mixture, we could have percent by mass. Percent by mass is not terribly convenient. So percent by mass is rare. Air. Do you know what the percent by mass oxygen is in air? Percent by mass is very convenient for other things like sugar water. Sugar water, we want to know how many grams of sugar for every 100 grams of sugar water. You know? So if I consume 100 grams of sugar water, how many grams of pure sugar did I just consume? For gases, it's much more convenient that we look at mole, percent by mole. So let's look at air as an example here. Air, if I think about air, air is about what percent oxygen? 20% oxygen. So air is about 20% O2. What happens if I heat up the air? Does that change? If I heat up the air or cool it down, would it change? In other words, if we're talking about mole, that means 20% of the molecules are oxygen, 80% are usually rather nitrogen. You know, so out of every 100 molecules of air, mixture, 20 of those molecules should be O2. Does that make sense? All right, this is the mole percent. We also have a fraction. This is 20 moles of O2 for every 100 moles of air. This is what we call a mole fraction. Mole fraction is what we use in dimensional analysis. Mole fraction. So that's percent by mole. Sorry. 2, 3, percent by pressure. It turns out that the mole percentage and the pressure percentage are the same. So if air is 20% O2 by pressure, so let's say I have a bar of air or 1 atmosphere of air. that means I'll have 0.2 atmospheres of O2 for every 1 atmosphere of air. The way we think about this is like this. The pressure is caused by collisions. So I'll have 80 molecules of nitrogen, let's say, colliding, and only 20 molecules of oxygen colliding. So what I'm going to do is I'm going to look at just the blue collisions. If I look at just the blue collisions, that's only a fraction of the collisions, total collisions. What fraction of the total collisions is that? 20 out of 100, or 0.2 out of 1. 0.2 out of 1 is 20 out of 100. So if I have 100 molecules of air, only 20 of them are oxygen colliding. So if I just look at the pressure generated by the blue, it's a fraction of the total pressure. What is the fraction? Well, this is the fraction. And the fraction depends on how many molecules I have colliding with the wall. Pressure fraction. This is Dalton's law of partial pressures. So the pressure of the air is equal to the pressure of the oxygen. The pressure of the oxygen is the blue collisions, plus I'm going to just simplify air into oxygen and nitrogen, plus the pressure of the nitrogen, which are the black. And so if air is 20% oxygen and 80% nitrogen, then I have 1 atmosphere of air that's going to equal 0.2 atmospheres of oxygen plus 0.8 atmospheres of nitrogen. Because the other 80% of the collisions is generated by nitrogen. And so this is called Dalton's law of partial pressures. That is, P total is equal to the sum of the partial pressures. And the pressure fractions are the same as the mole fractions here. We have one more. This is not in your book though. This is the percent by volume. In other words, look at the mole fraction. Mole fraction is 20 out of 100. The pressure fraction is 20 out of 100. It turns out the volume fraction is 20 out of 100. The mass fraction is not, because the mass fraction of the mass percentage is different. And so the percent by volume is the same. 20 liters of O2 for every 100 liters of air. True. But both 3 and 4 cannot be true simultaneously. So 100 liters of air will contain 20 liters of oxygen and 80 liters of nitrogen. Dalton's law is if we have constant volume. This is a fan. So true if constant volume. And so what 3 and 4 are 2 ways of looking at the exact same mixture, but we visualize them differently. And so let's take a look at 3 and 4 in detail. air, and I'm going to go with 100 liters of air. This is going to be a, should we do bar or atmosphere? What do you want to do? 1 bar or 1 atmosphere? 1 atmosphere? Not 1 atmosphere. The mole fraction is always true. There's going to be 80% of the molecules present here will be nitrogen. We'll do nitrogen left. And then 20% of the molecules in here will be oxygen, which will be blue. Now there are 2 ways we could visualize this mixture. So one way is the Dalton's mixture. Dalton's mixture is going to say this 100 liters of air consists of nitrogen and oxygen. In other words, 100 liters of air consists of 100 liters of oxygen. And so if I just remove the oxygen here, place that into a 100 liter box, am I going to have nearly the same number of collisions? No. And so this is going to be 100 liters of oxygen at 0.8 atmosphere. Or not 0.8, 0.2 atmosphere. You see, because I have so few collisions there. And then I'm also going to have 100 liters of nitrogen. But I have a lot more nitrogen in here. So I have a separate box of nitrogen. The nitrogen is going to be at what? How many atmospheres? 0.8 atmospheres. So we have Dalton's law. Dalton's law says this: P total is equal to P1 plus P2. That's it. The other way I could look at this is as an Avogadro's mixture. For Avogadro's mixture, what I want to do is I want to make it the constant pressure. In other words, I don't want the pressure to change. So Dalton's mixture is what we call a constant volume mixture. Constant volume means this. I have 100 liters of oxygen plus 100 liters of nitrogen. If I take 100 liters of oxygen and combine it with 100 liters of oxygen, how many liters of air will I get? 100 liters plus 100 liters should give me 200 liters, but it doesn't. Because what I do is I take these and combine them into one box. If I take these and combine it into one box, I get 100 liters of air at 1 atmosphere. So this is what we call constant volume. The volume doesn't change. In other words, the volume of air is equal to the volume of O2, which is equal to the volume of N2. And so the volume of air is equal to the volume of O2, which is equal to the volume of N2. We call that constant volume. The volume is always the same for everything. For Avogadro's, we call this constant pressure. It's exactly the same. I mean, it's 100 liters of air. but we just visualize it differently. So if I'm thinking in terms of Daltons, you know, if I have 100 liters of air, how many liters of O2 do I have? Oh, 100 liters. How many liters of N2 do I have? 100 liters. So what's the difference? The difference is the pressures. For Avogadro's, I want constant pressure. Actually, it's the exact same mixture. And so this is Avogadro's here. Let's carry it. So for Avogadro's, in order to get oxygen out 1 atmosphere, the only way I could do that is if I shrink down the box. And so I don't want a 100-liter box. I'm going to go way smaller. I'm going to go to a 20-liter box. If I shrink this down to a 20-liter box, so I go from 100 liters to 20 liters. What that's going to do is going to a lot of oxygen in a smaller volume. And it turns out that if I shrink it from 100 liters to 20 liters, the pressure increases. The pressure increases to 1 atmosphere. And so I have 20 liters of oxygen at 1 atmosphere. If I expand this box to 100 liters, then the pressure is going to decrease to 0.2 atmosphere. So I have 20 liters of oxygen at 1 atmosphere. How many liters of nitrogen do I have? 80. I'm going to have 80 liters of nitrogen at how many atmospheres? At 1 atmosphere. So we have Avogadro's law. Avogadro's law says that V total is equal to V1 plus V2. So 20 liters plus 80 liters makes 100 liters. But Avogadro's law also says that P for air is equal to P for O2, which is equal to P for N2. So if I'm thinking in terms of Avogadro's law, how many atmospheres of nitrogen do I have? 1. How many atmospheres of oxygen do I have? 1. So 1 atmosphere of nitrogen plus 1 atmosphere of oxygen should make 2 atmospheres of air, right? But it doesn't. 1 atmosphere of oxygen plus 1 atmosphere of nitrogen makes 1 atmosphere of air. What's different is the volumes. The volumes are additive with Avogadro's law. The pressures are additive with Dalton's. So what we're going to do is we're going to just focus on Dalton's here. When we focus on Dalton's, then the volumes are all the same. The difference is the pressures. So there should be one more equation below this. V total is equal to V1, which is equal to V2, which is equal to V3. So what's the volume of gas 1? Well, it's the same as the volume of every other gas, including the total mixture. A scientist sets up an artificial atmosphere with 4 gases. Their partial pressures are 0.78 bars of nitrogen, 0.21 bars of oxygen, 0.09 bars of argon, and 0.025 bars of water. What is the total pressure? We'll just add them all up, you know? You add them all up, then that's the total pressure. follow. 1.02 bar. So what Dalton says is the total pressure is equal to the sum of the individual pressures. Just add them up. So Dalton's law, is that a hard equation? It's pretty easy. From the language it seems pretty hard. Experimental apparatus to demonstrate Dalton's law of partial pressures. So what do we do with the volume? They're all the same. 1 liter flask. This one is 1 liter flask. This one is a 1 liter flask. They screwed this up because the volume's got to be exactly the same. The volumes have changed here. Do you see the volumes changed? I'd rather skip this. The volumes just changed a little bit, you know. You see the volumes changed a little bit. To do this properly, the volume should not change at all. And then, you know, if you take this nitrogen and compress it into one container, you know, what we're doing is we're taking the nitrogen and oxygen and compressing this into the same size container. The pressure is going to increase. Now we have a lot more molecules in here. And so here the pressure was 186. Here the pressure is 93. Here the pressure is going to be 186 plus 93 because now we got both gases in one container. So that's Dalton's law. It's kind of overly complex. And they made it overly complex and they still didn't make it accurate. So it's very simple. This is it. You take this container of nitrogen and force it into this container of oxygen. Or take this container of oxygen and force it into this nitrogen. So we'll take all that oxygen and force it into this container. We're going to get the same size, 100 liters of air. The pressure is going to be 1 atmosphere. Combined pressures. Here's an application of Dalton's law. Probably this is this is another application of Dalton's law. But in this application of Dalton's law, this is gases generated. Sometimes what we do with the gases, like for example oxygen, we might generate some oxygen and we might bubble it through water. Have you ever been inside an indoor swimming pool? You know, it's humid inside, isn't it? Do you feel that humidity? Or bath, you know, if you set up a bath and the bathroom, close all the doors, it gets humid inside there, right? Will the humidity increase and continue to increase? Or does the humidity plateau at some point? It actually plateaus. When it plateaus, we call it 100% relative humidity. And so the humidity will increase like in your bathroom or something. Humidity increases, and eventually it hits 100% relative humidity. At 100% relative humidity, that's as humid as it's going to get. Is the air today at 100% relative humidity? No. But if I took the air in this room and then made a little pump, an air pump, so I'm going to take all the air in this room and bubble it through a pool of water, then what's going to happen is the air is going to get saturated with water vapor. In other words, the air is going to pick up water, moisture. And so if I took the air in this room and start bubbling it through water, eventually this room is going to become 100% saturated with water vapor. In other words, 100% relative humidity. And so this is what's happening here. If we take a gas and we generate it and we bubble it through water, the gas here is saturated with water vapor. That is, this oxygen is not dry. what we say is this oxygen is wet. It's wet with humidity. You know, you can feel the air. If you go out to the desert, the air is dry, right? When you go out to the ocean, the air is a lot more humid. If you go to the East Coast, then you might hit 100% relative humidity. It'd be miserable because it's uncomfortable. Because we can't regulate our body temperature. The air is saturated. And so this is not dry oxygen. This is not pure oxygen. This is oxygen that's been saturated with water vapor because we're bubbling it through the water. Well, it's a mixture of gases. We have oxygen gas and water gas. Water vapor. And so the pressure that's generated inside here is a combination of the oxygen plus the water vapor. The water vapor is going to collide with the walls, generating pressure too. And so if I measure the pressure inside here, well, I'm not measuring the pressure of pure oxygen. I'm measuring the pressure of pure oxygen plus water vapor. What's this saying? Water levels inside and outside the test tube are the same, equalize the pressure. And so if the water level inside the test tube here were the same as the water level outside, then we have a balanced seesaw. And so let's say this is outside the test tube, this is inside the test tube. If they're at the same level, then they weigh the same amount. Pressure can be thought of as weight. Weight of the atmosphere, the weight of if their levels aren't the same, let's say inside the test tube is lower, then we have higher pressure inside, lower pressure outside. Or if the outside level is lower, then we have higher pressure outside, lower pressure inside. So we want the two pressures equal. Do you remember doing this in lab? Remember plugging something up and then dipping it in the sink and then just eyeballing it? That's called equalization of pressures. And so what we can do is we know the pressure outside. The pressure outside of the test tube out here can be measured using an instrument. What's that instrument called? If we want to measure the room pressure, we use it's mounted on the wall. It's called a what? I know it's been a while. It's easy to forget. Because that was way back in chapter 4. Way back in chapter 4, all that stuff is, well, not all of it, but a lot of it's long since disappeared from your memory, perhaps. The problem is you'll need to know it for the final. If the final were not cumulative, then no big deal. You'll forget everything from the beginning of the class. So the final is going to be cumulative. So what's that instrument called? Barometer. So this is how we measure the pressure outside. Barometer. Chapter 4. Let's go back to chapter 15. So we know what the pressure is outside. The pressure outside is the same as the pressure inside because the two levels are equal. And so we know what the total pressure of this gas is. What we want to figure out is we want to figure out what the pressure of the gas, what the pressure of the O2 is. We can do that if we know the pressure of water. We know the pressure of water. We know the pressure of water because we know what 100% relative humidity is. And 100% relative humidity varies with temperature. And so how humid it is depends on the temperature. You know, if it's freezing cold outside, we can't put too much water in the air. If it's hot, we can put a lot of water in there. And the hotter it is, the more water we can get in the air. I want to jump ahead here for a second. Talk about that. You know, on a particulate level, the hotter it is, the more these water molecules can escape off the surface and vaporize. And therefore, if we cap this, pretty soon the air in here is going to be saturated with water vapor, and it's going to stop. Because we have two processes. It's called a dynamic equilibrium. In the dynamic equilibrium, we have vaporization, which is these up arrows. At the same time we have vaporization, we have condensation, because a water molecule can come back here and strike the surface. If it strikes the surface and sticks, we call that condensation. So initially, when we have less than 100% relative humidity, we have net vaporization. Things can become more and more humid. But eventually what's going to happen is the more water molecules we get, the more condensation we get, and we get a balance. That is, we hit a point where the vaporization is equal to the condensation. And then we can't vaporize anymore, because even if we try to vaporize more, we'll condense more. And we've reached this state of equilibrium where it doesn't change. This is called dynamic equilibrium. Well, how much we vaporize depends on the temperature. So here we are. Now, let's say we have a temperature. Right now, let's say the air is dry. Air is dry, what's going to happen is there's going to be net vaporization. Very little condensation, because we just don't have that many water molecules in gas in the state. But as we vaporize more and more, we're going to increase the condensation, because there's more that can strike back. Eventually, we're going to hit this, where the vaporization rate equals the condensation rate, and no further change occurred. That is, we've saturated the air. When we saturated the air, that's called 100% relative humidity air. And there's no further change. Well, that's no further change at the macroscopic level. The relative humidity stays the same, but at the particulate level, there's change. Because condensation and vaporization never stop. These are always going. And so what we call this is, we call this a dynamic equilibrium. Dynamic at the particulate level, equilibrium means no change. Dynamic means change. And so it's dynamic at the particulate level because it's happening. But it's just spinning wheels here because there's no net change. This is like you're riding your bicycle, but the rear tire is lifted off the ground, so you're just spinning your wheels. So it's dynamic, the wheel's spinning, but you're not moving anywhere. So you're at equilibrium, dynamic equilibrium. Well, that depends on the temperature. So this is what we see with relative humidity. This is relative humidity measured in pressure. And so the higher the temperature of the water, the higher the relative humidity. Or not relative, the higher the absolute humidity. Relative humidity is always what percentage are you here. And so if we look at the absolute humidity at 60 degrees C will be this much water. The relative humidity is the air, does the air contain that much water? And so the relative humidity, well, it does change because of the size, the absolute humidity here. And so what we do is we take this graph here. There are three things we could do. One, we can determine it, these are from measurements. We can determine the humidity, the absolute humidity based on this graph. Two, we can describe this graph as a mathematical equation and calculate the humidity based on this equation. Or three, we can just put a whole bunch of XY data into a table and use that. Well, what method are we going to use? We're going to use method 3. We're going to take that graph and just look at the original data. we look at the original data, then it's not in here. I have to go online and show you what it is. Let me show you what it is. This is called the vapor pressure water table. You want the table. And so this is going to be in tabular form. Look at these table here. We can find lots of these tables online. We'll find one here. So slow. Something's wrong with this. Okay, I'll just use this one. So what we can do is what we could do is we could just look at a table like this. And so when the air becomes saturated, or when the gas becomes saturated with water, it'll hit these limits. So for example, at 25 degrees C, we're going to generate 23.8 millimeters of mercury pressure just from the water. Just from the water. And so that holds for any size container. So, so I jumped ahead there. Let me jump back where we were. So this is calculate the partial pressure of oxygen in atmospheres in a sample collected over water. Well, any sample collected over water, we're going to assume is 100% saturated with water vapor. In other words, we're going to assume that sample of oxygen is at 100% relative humidity. Given that the total pressure of the mixture is 0.98 atmospheres and the partial pressure of water vapor, so at this temperature, the water vapor is going to exert 16.5 millimeters of mercury pressure. And so what we do is this. We have basically it's Dalton mixture. So here we're going to have oxygen. This time I'm going to make oxygen black. And we have water vapor. Just a little bit, you know, this is going to be saturated at 100% relative humidity. So this is water vapor. Yeah. Well, we can know how much water vapor there is in air because this just depends on temperature. So this is 100% relative humidity. In other words, it's saturated, what we call saturated with water vapor. That just depends on the temperature. And so we can figure out the collisions that are generated from that. And so at this temperature, the pressure of the water gas is 16.5 millimeters of mercury. What is the temperature? We can figure out what the temperature is. Let me just go back to this. 16.5, the temperature must be 19 degrees C. Because at 19 degrees C, the water pressure should be 16.5 millimeters of mercury. So this has got to be at 19 degrees C. At different temperatures, higher temperatures will get more water vapor, and lower temperatures will get less water vapor. And so we know the total pressure of the mixture. And so what we want to do is we want to figure out the pressure of the oxygen. And so the pressure of the mixture is given. .98 atmospheres. And the pressure of the mixture is going to equal the pressure of the oxygen plus the pressure of the water vapor. There are only two things in this mixture. And so we know what the pressure of the water vapor is. So this 0.9 atmospheres is equal to the pressure of the oxygen plus the water vapor is 16.5 millimeters of mercury. In other words, the pressure of the oxygen is equal to the pressure of the mixture, and we got to just subtract out the pressure of the water vapor. So if we look at the pressure of the mixture minus the pressure of the water vapor, we can get the pressure of the oxygen. However, the units aren't the same. So what do they want? Do we want to do it in millimeters of mercury or atmospheres? Let's do it in atmospheres. And so what we're going to do is we're going to convert millimeters of mercury to atmospheres. 1 ATM equal to 760 millimeters of mercury by definition. And so this is going to be 0.98 atmospheres total minus 16.5 divided by 760. 16.5 divided by 760. 0.0217 minus 0.0217 0.02171 atmospheres. Comes out to 0.958. Comes out to 0.958 atmospheres of O2. And so this mixture consists of about 0.96 atmospheres of O2 and 0.02 atmospheres of water vapor. So they're doing it in atmospheres too. So we have 0.96. So in other words, here, 0.96 atmospheres of oxygen plus 0.02 atmospheres of water yields 0.98 atmospheres total. That's Dalton's law. And so that's an application of Dalton's law. Whenever we collect gases over water, the gases become saturated with water vapor. So we have to worry about that water vapor. We can figure out how much water vapor there is because humidity just depends on temperature. Okay, comparison of properties of liquids with properties of gases. These are just the macroscopic properties. Gases can be compressed, liquids cannot. Gases can expand to fill the containers, liquids do not. Gases have low density, liquids have much higher densities, 1,000 times higher typically. Gases may be mixed in a fixed volume, liquids cannot. For example, we take 100 liters of nitrogen with 100 liters of oxygen, we can make 100 liters of air, no problem. However, if you take 100 milliliters of sugar water and combine it with 100 milliliters of salt water, you're going to get 200 milliliters. You can't make 100 milliliters of sugar salt water, can you? Gases exert constant pressure on the walls of their container uniformly in all directions. Pressure in the liquid container increases with increasing depth. The deeper. In the gases, it doesn't matter if it's the ceiling or the floor. In a liquid, the floor is going to be at the highest pressure in the bottom of the pool. All right, when we talk about liquids, there are certain things that you need to know. One is vapor pressure. This thing is called the vapor pressure of water. Here. Vapor pressure is the pressure or partial pressure exerted by vapor that is in contact with the liquid phase. If the gas space above the liquid is closed, the vapor pressure increases to a definite value called the equilibrium vapor pressure. The equilibrium vapor pressure is 100% relative humidity. Stronger the intermolecular attractive forces, the fewer number of molecules in the gaseous state. So we're looking at, what does the vapor pressure depend on? There are certain things that are volatile and there's certain things that aren't. Water is somewhat volatile, that is, the water molecules volatilize on the surface here. Alcohol is much more volatile. The alcohol molecules will evaporate much easier. Syrup is much less volatile. Syrup doesn't really, and so the more that volatilizes off, the greater the humidity here, the greater the vapor pressure. And so in other words, the higher the vapor pressure, the more volatile, the lower the vapor pressure, the less volatile at a given temperature. And so it depends on the intermolecular forces. The intermolecular forces are what's holding the water molecules together. And so in order to escape off the surface, we have to break the intermolecular forces and hold it. And so the stronger the intermolecular forces, the less volatile. The weaker the intermolecular forces, the more volatile. The more volatile, the higher the vapor pressure. The less volatile, the lower the vapor pressure. So let's see what it says here. Some of the liquid phase molecules are moving with a kinetic energy large enough to overcome the intermolecular attractions in the liquid and escape to the gas phase. And so just at 25 degrees C, some of these water molecules have enough energy to break free. Most of them don't. Most of them are stuck. At the same time, some molecules in the gas phase re-enter liquid. That is, they go here and they get stuck. The intermolecular forces are like glue or sticky adhesive right there. So if they're not moving too fast, they can get stuck and condense. See this